run a program, all the neural network descriptions programs are loaded into SRAM at the start, and then they sit there ready to go all the time. So to run a network, you have to program the address of the input buffer, which presumably is a new image that just arrived from a camera. You set the output buffer address, you set the pointer to the network weights, and then you set go. And then the machine goes off and will sequence through the entire neural network all by itself, usually running for 1 million or 2 million cycles. And then when it's done, you get an interrupt and can post-process the results. So moving on to results. We had a goal to stay under 100 watts. This is measured data from cars driving around running the full autopilot stack. And we're dissipating 72 watts, which is a little bit more power than the previous design, but with the dramatic improvement in performance, it's still a pretty good answer. Of that 72 watts, about 15 watts is being consumed running the neural networks. In terms of cost, the silicon cost of this solution is about 80% of what we were paying before. So we are saving money by switching to this solution. And in terms of performance, we took the narrow camera neural network, which I've been talking about, that has 35 billion operations in it. We ran it on the old hardware in a loop as quick as possible, and we delivered 110 frames per second. We took the same data, the same network, compiled it for hardware for the new FSD computer, and using all 4 accelerators, we can get 2,300 frames per second processed. So a factor of 21.
I think this is perhaps the most significant slide. It's night and day.
I've never worked on a project where the performance increase was more than 3. So this was pretty fun. If you compare it to, say, NVIDIA's Drive Xavier solution, a single chip delivers 21 teraops. Our full self-driving computer with 2 chips is 144 teraops.